Perfect.
Right, so I'd like to, it's a pleasure to introduce Steve Miller from Williams College. And there are a couple of things I want to say about Steve. One is that he used to be faculty member here, and all of the rest of us used to hunker down because he was so popular that we all looked bad. Then the other thing I want to say is that he is a member of a group at Williams who runs the small summer program for undergraduates, who keeps that group, and Steve among them, keeps churning out undergraduates who produce math papers and then go on to grad school. One of the best methods for me to select graduate students when I was director of graduate studies was to call up Steve and ask him about recommendations.
The 12 letters I would send you each year.
In the 12 letters. So now Steve added a third thing that I must tell you, which is that he's a Red Sox fan.
Yes.
And he's, I could say he's a rabid Red Sox fan. But I'll stop here and let him take over.
So thank you. It's always fun to be back. I taught 162 for 4 years here and had a lot of fun teaching that course. There are two really fun topics that I could have discussed today. One is actually about baseball mathematics, but I decided based on who my host is, I would go for Benford's law instead. And so as Dan has said, I am a professor at Williams College. We have a very large summer REU program, research experience for undergraduates. We've had several Brown students over the past few years. If you're interested in a career in mathematics, it's a really good idea to try your hand at summer research and see how much you enjoy it. And so the stuff I'm going to talk about today actually leads to some open problems that I'll be looking at with students this summer. I'm also going to be giving a talk at the Doug at 4 p.m. on another theme of my research, which, again, I'll be soliciting applications for. So if you're interested in any of this, please let me know. Please feel free to speak up throughout the talk. The purpose is to have some fun and to see some interesting connections of probability with real-world applications. Okay. So here's what I think is an interesting question to start the day with. So imagine you have some nice data set. Maybe it's the Fibonacci numbers, maybe it's stock prices, maybe I somehow go through Banner and access your home addresses and find out what streets you live on and what number do you live on. I make a compilation of all these numbers. And a natural question to ask is, what percent of the time is the first digit going to be a 1? So do I have any guesses? What's the most obvious naive guess? I don't care if it's wrong, I hope it's wrong. 10%. 10%, perfect. No, okay, plausible answer 10%. Now all of a sudden you realize, oh, it can't be 10%. Okay, good, we don't have any zeros, so what are you correct to? 1 over 9 or 11%. The actual answer is, for many data sets, it's about 30%. And I'll give you a proof later for the Fibonacci numbers, modulo one nice fact from number theory. I really am a number theorist, even though I do a lot of stuff in probability. I do it with a very number theoretic flavor. 30% of the Fibonacci numbers start with a 1. By some strange chance, if you get bored during this talk, just start writing Fibonacci numbers down, see how far you can go, and start tabulating them. It should be close to 30%. Right, so what am I going to do today? I'm going to state Benford's law of digit bias. I'll give some examples and applications. I'll sketch some proofs. And then if there's time at the end, I'll describe some open problems. And one of the things I really like about this topic is to get far into it, you don't need to know that much. First course in probability is all you really need. People working in this field come from all over the place. There's statisticians, there's engineers, there's physicists, there's mathematicians, there's accountants. And so one of my favorite stories is when I was a very young postdoc, I had only 1 or 2 papers published, and I get an email, and it begins, "Greetings, my name is David Kelly. I'm a senior criminal investigator at the IRS." And my head just goes down, and eventually some of my friends come by, "What's going on, Steve? I don't want to talk about it." And it took me about 5 or 10 minutes before I could read the rest of the email, because this was not the first time I've had a run-in with the IRS. We'll talk later as to why I actually had to leave Brown. But the next line of the email was, "I recently read with interest your paper in Acta Arithmetica." And I was such a newly minted PhD, the fact that anybody could read, with interest just at all, just read one of my papers was just shocking. And so one of the greatest applications of Benford's law is for the IRS. And so depending on your point of view, I will show you how you can use the Riemann Zeta function to either help the IRS or to thwart the IRS. Yes?
You just told us about another application, the career of young mathematicians.
Yes. Yes, you can look at how many papers I'm publishing to see if it's actually reasonable that these are all legitimate papers by the distribution of how many papers I've written each year. So my little guest here is Al Capone. He's actually a gift from the Internal Revenue Service. I have to make sure I bring him to the talks so that he's actually being used for business purposes and not personal. But I actually gave a talk at the Boston headquarters of the IRS. It's the only talk I've been in with an armed audience. And it was a very interesting experience talking to the IRS about the mathematics behind Benford's law. For good or for ill, the IRS has very limited resources. And they have to decide how to allocate them most effectively. And that's where a lot of the stuff is going to come into play. So just before we get into the details, a little bit of a warning. So a test indicating fraud is not proof of fraud. Unlikely events can happen for alternative reasons. So the IRS cares about Benford's law. That's the main implication, the main application of all the stuff today, is the IRS likes to use this to detect tax fraud. But just because a math test indicates something suspicious might be happening is not proof that something suspicious is actually happening. So one of my favorite comic strips is Dilbert. Dilbert is one of the strips that either people love or hate. Your travel expenses are rejected because all of your meal costs are round numbers. You're a liar or worse. I decided what to order based on what totals to a round number after a 15% tip. That's worse. My later talk today in the Doug is actually going to be based on a reimbursement of mine that was denied by Williams College for a $2.70 lunch in New York City. And so this stuff about dealing with receipts is extremely important. How many of you are planning a career in business? You know, in the real world. So a lot of times if you're in the real world and you're traveling for a company, you get a certain allowance. And you can have a lunch up to $25 without having to submit a receipt. Over $25 you need a receipt. How much are most lunches?
$24.90.
$24.90, $24.95, $24.30, you know, something 24 and change, as people are basically trying to pad their expense, get a little extra money back. So there are certain numbers you expect to have strange distributions. Alright, so what's Benford's law? So for many data sets, the probability of observing a first digit of d base b is log of b, d plus 1 over d. So base 10, this means about 30% of the numbers are 1. So if you have a probability distribution, there's two things to check. Is it non-negative, and does it sum to 1? Well, if I'm looking at base 10, the log base 10 of d plus 1 over d, and I want to sum this, d goes from 1 to 9. Well, perfectly aligned with the straight vertical. Well, what's the sum of a log? The log of the products. So this is now the same as the log base 10 of 2 over 1 times 3 over 2 all the way down to 10 over 9. So everything's going to cancel, and you'll be left with the log of 10 base 10, which will be 1. So this is at least a probability distribution. You know, it's non-negative, it sums to 1. And so the question is, why do so many data sets satisfy this bias? Well, not every set will satisfy Benford's law. So I gave you one example already, you know, receipts of business travelers. There's going to be a huge concentration around 24. Here's another fun example. Imagine you have a long street. So the houses on the street are labeled 1, 2, 3, all the way up to L. Well, depending on what L is, you're going to get a very different distribution for the leading digit. So if L is 199, you're going to have a huge number of houses on the street starting with a 1. In fact, over 50%, because everything from 100 to 199 is going to start with a 1. Conversely, if L is 999, you're going to have a very small percent of numbers that will start with a 1. And so in a situation like this, it's going to be very non-Benford. What does become Benford is if you have many streets of different sizes. And so Benford's law is often going to happen in an amalgamation of data sets. And so almost surely all of you are not coming from the same street in the same city in the same state. And so you'll all be from streets with different lengths. And it's very likely, if we look at the distribution of digits of your streets, it would be close to Benford. And this whole idea of why is this amalgamation going on There's lots of different ways to look at it. So I'm going to try to give you, later in the talk, a central limit theorem perspective as to why this Benford law is going on. And so if you look at things appropriately, you have sums of random variables, the central limit theorem is going to kick in, and it's going to control the behavior. There's going to be a couple of change of variables we're going to need to do. I know when I teach probability, the change of variable theorem from Calc 3 is one of the things my students hate the most. Is they're not that comfortable, they don't always remember all the Jacobians and all that stuff. But really, that's what's going on here, is if you change your perspective appropriately, you're in a situation where the central limit theorem kicks in. And that's going to control the limiting behavior. And we're just going to have to do some bookkeeping to get to that stage. All right, so here's a bunch of examples where Benford's law comes into play. So the first is recurrence relations. These are things like the Fibonacci numbers, fn plus 1 equals fn plus fn minus 1. We'll talk about this in great detail. How many of you have ever played roulette? All right, so I guess it's just one. So do you know the strategy double plus 1?
No.
So you bet $1 on black. If it comes up black, you net $1. If not, you bet $2. If it comes up black, you net $1. If not, you're down 3. You bet $4. You keep doubling, and then eventually you net $1. There's a reason why this strategy doesn't work. Don't go home and try this until you talk to me. When I taught 162, we tried to convince someone not to use this strategy and could not. Recurrence relations actually explain why the strategy doesn't work. And so recurrence relations are discrete versions of differential equations. So if you've taken a physics course, you know everything is modeled by differential equations. Recurrence relations are discrete versions of this. This gives you some sense of why Benford's law is so important. A lot of special functions satisfy Benford's law. Another thing is iterations of power, exponential, and rational maps. For me, the most important one is products of random variables. And so, usually in a probability class, you haven't done too much with products. You've basically been doing sums of random variables. You know, imagine it's your lucky day and I'm going to give you a block of gold. Okay? You want to figure out how much money you have, what do you need? What do you need to know?
The price of gold.
Price of gold, what else? And so how would you figure out how much gold? Density, and then what? Dimensions. So length, width, height, price. So there's 4 multiplications going on together. And so if I want to figure out how much this gold bar is worth, I can say I'm going to have a product of 4 random variables. How many of you are potential econ people? Okay. Seeming to be a correlation. So in economics, you're going to have very complicated functions that are going to be products and functions of various random variables. And so this idea of products of random variables really comes into play and explains why we see so many Benford places. Then there's a bunch of other stuff down here, some number theory stuff, some Bayesian analysis. The real one that the IRS cares about is financial data. Corporations, if you look at the tax returns of corporations, they do a really good job of following Benford's law. Individual tax returns don't. Anybody have any idea of what's the difference between an individual return and a corporate return? There's lots of differences. Yes?
Like corporate, either like expenditures or incomes will be like multiple different scales of like, you might have like, you'll get $15 from something, then maybe it'll make like a $3,000 sale.
Good.
And then, but for a person, it's not as many.
Right, you're not going to have as many data points. So an individual is going to have very few data points, and it's going to be somewhat concentrated. Whereas a corporation is going to have thousands of data entries over many different scales. So you have a chance for this amalgamation, and the Benford is going to set in. So the IRS cannot really do anything against individuals. They can actually prove that individuals cheat as a group, but they can't prove individuals, specific individuals, are cheating by Benford's law. So anybody know what a good category is for individual cheating? It's good that you can't answer these so quickly. Charitable deductions. How much are the clothes or whatnot that you're donating to charity worth? And now the IRS is often requiring people to attach documentation as to how much the clothes you've donated to charity are worth. And so for a lot of us, it's like, I don't need the $15 deduction, just ignore that. It's just not worth the paperwork. But if you look at the distribution of these categories over all individuals, the numbers look suspicious. But for an individual, there's not enough data for the IRS to attack an individual. For a corporation, there is. One of my wife's cousins, yes?
So we just did that in this last year.
Oh, did you?
So we had lots of bags of clothes, and our tax preparers said, well, if it's under $500, you don't need to
Right.
match anything. So we made it under $500.
$495.18.
Something like that.
Something like that, yes. So thank you for proving the point as to exactly how much people claim. One of my wife's cousins is an accountant, and they actually now run Benford's Law test on the data they get from corporations before they file tax returns. And if the numbers are suspicious, they actually contact their client and say, are you sure you gave us the right numbers to analyze? And so, it's very interesting. The IRS tries to use this as a flag to figure out which company is worth auditing. So of course, now the companies that are smart know the IRS is doing this, or at least has the potential to do this. And so then these companies should actually then make sure that their data passes the test. So a couple of years ago, two of my small students and I came up with a way to detect certain types of tax fraud that would pass Benford tests. And so we've given this to the IRS, which is moving almost as fast as molasses. But we said, we are happy to give you this method for free. We think it's worthwhile for us to have friends in the IRS for later in life. We don't need any compensation. And so, it's slowly working through the different systems there about having them try to actually apply this to something. But the IRS really is looking for ways to efficiently determine which corporations to audit in detail. Okay, how many of you have seen the Riemann Zeta function? Right, good. A lot of hands going up on this one. This is one of my favorite functions in mathematics. I am primarily a number theorist. So the Riemann Zeta function is defined as the sum of 1 over n to the s, where n ranges over all the integers. It's the same as the product over all primes of 1 minus 1 over p to the s inverse. To prove this is basically the fundamental theme of arithmetic. Every integer can be written uniquely as a power of primes. And everything converges so long as the real part of s is greater than 1. Right, I need a volunteer. Alright, what's the next integer after 2012?
2013.
Thank you, I need another volunteer. What's the next prime after 2012? Okay, thank you. So the integers are extremely well understood. Either that or there's a difference in terms of mathematical ability in this class. And it's very easy to get the next integer from a given integer. The primes are a bit more mysterious. The reason why we care so much about this function is we can use it to take information about the integers and pass information about the primes. And so one of the interesting questions to ask is, how are the values of this function distributed? And so I'm not going to go into all the details. It pains me not to go into all the details. I'm happy to chat more about this. But it turns out the most important places to evaluate this function are when s is equal to 1/2 plus an imaginary number. And for those of you who worry that the series doesn't converge when s is less than 1, ignore that for now. There's a way to continue this and have this make sense. And so I'm going to just evaluate this function at 65,535 evenly spaced points on this critical line. And here's a plot. I forget which ones are the Benford predictions and which ones are the values of the Riemann Zeta function, because I don't really have to worry about which one is which. The fit is that good. The values of the Riemann Zeta function provide a wonderful data set that's Benford. So in terms of trying to find false data for to fool the IRS, this is being recorded. I will stop there. Okay. So applications. So I've already talked a lot about tax fraud. Another one is image fraud. As Professor Vramovich has said, I am a Red Sox fan. I have sadly made my children Red Sox fans as well. I remember years ago when I was young watching the news the day after a Red Sox game, and then the scandal that followed the next day. One of the networks had broadcast the Red Sox game. Another network was then showing clips of the Red Sox game on the nightly news, and they removed the logo from the channel that was broadcasting the Red Sox game. And of course the channel that was broadcasting the Red Sox game was very upset that their logo had been removed from the image. So how do you know if an image has been modified or not? One of the nice applications of Benford's law is detecting image fraud. Has somebody modified images? Is anybody here in Professor Silverman? No, Professor Silverman is teaching cryptography right now, so no one is in that crypto class. Okay. Another application is in computer science. Are there any computer scientists here? So a lot of it is in terms of analyzing round-off errors when you're doing operations, or the optimal ways to store numbers. So to try to minimize the number of operations you have to do. Turns out Benford's law has some really nice applications to this in, you know, I'm blanking, is it Knapp's theory of computation? I'm sorry, the art of programming? In the art of programming, he actually had, and I think it's volume 2, he has a section on Benford's law and applications.
Could you talk about the image fraud again? How Benford's law applies?
Sure. What happens is, it's a little technical. If you take the image and you look at like the discrete Fourier transform, and you look at the distribution of the Fourier coefficients in the discrete Fourier transform space, there's basically a Benford's law behavior for the coefficients there.
Okay.
And so it's a little bit technical, but you know, if you send me an email, my address is, actually, I can still use my Brown address. Brown is extremely nice at math.brown.edu. And as long as not too many people advertise that this address still works, it should still continue to work for a while. I'm actually editing the first book on Benford's law right now. And if anybody is interested in helping me, we have a lot of submissions in many different fields, including a field on image fraud. And so I'm looking for people to help me in terms of editing the book. All right. So we've been, blabbing for about, 22 minutes. It's probably time to get into some general theory. Why is Benford's law true? All right. So I need to review some old scientific notation. Some people call this mantisses. Some people call this the significand. There's a dispute between the engineers and a few other people. Basically, it's scientific notation. You give me any number, and I can write it as, some number between 1 and 10, and then 10 to an integer power. So 10 to the k is going to basically pad zeros. Either zeros to the left or right of the decimal point. And then I can always adjust it so that this number is going to be between 1 and 10. So if I give you the number 2012, I would write that as 2.012 times 10 to the 3. Okay. So two numbers have the same mantissa if they have the same leading digit. And essentially, well, the only place they're going to change is how many zeros I'm padding with. And so here's the key observation. If I take my numbers, x and x tilde, and I take the log base 10, and then I look at things modulo 1. So how many of you have taken abstract algebra? Okay, if you haven't taken abstract algebra, if it's 11 o'clock now, what time will it be in 4 hours? 3. So everybody has told me that 11 plus 4 equals 3. Right? And so we write 11 is congruent to 3 mod 12. And what this means is 11 minus...
Pardon me?
15. Yeah, I was going to say. 4 hours from now is 15. And that means 15 minus 3 is a multiple of 12. So two numbers are equivalent on the clock if they differ by a multiple of 12. So what we're doing here is we're looking at a clock with just 1 hour. And we're saying these two numbers are the same mod 1, modulo 1, if they differ by a multiple of 1, integer multiple of 1. Well, if I take the log of my number x, I'm going to get the log of the mantissa plus k. And for the other one, I'd get the log of its mantissa plus k tilde, another integer. This is explaining why the logarithm is so useful for studying Benford law problems. If I want to study the distribution of my digits, if all I care about is my leading digits, I don't care about k. All k does is pad how many zeros I have. So I want a process that will get rid of the k. And the way I do this is I take the logarithm and then I just chop off the integer part. And because this number is between 1 and 10, the log of 1 is 0, the log of 10 is 1. The log of this is going to be a number between 0 and 1. And I'm going to get plus k. So when I look at this mod 1, I get a number between 0 and 1. So I now have a mapping that you give me any integer, you give me any real number, and I will return a number between 0 and 1. So I've got to be a little careful. If my number is negative, I should put in absolute values first. If my number is 0, everything blows up. So I have to just stay away from looking at what's the leading digit of 0. Well, 0 doesn't really have a leading digit in some sense. Or if you want, it's the unique number whose leading digit, in fact, all digits are just 0. So the key observation is two numbers are equal if you look at their logs base 10 modulo 1, if and only if they have the same leading digit. So instead of studying my original number x, I'm going to study this transform. And you can begin to see where some of the stuff, from Calc 3, these change of variable formulas, are going to come into play. So the first concept we now need is that of equidistribution. And if you've seen the uniform distribution, another phrase is things are uniformly distributed. So I give you a sequence of numbers, yn, and I'll say it's equidistributed modulo 1 if the probability it takes on a value in an interval ab tends to b minus a. So what does this mean? Well, let's let n be some large number, and let's see what fraction of the time do I land in the interval. So I count how many times I'm in the interval, and I divide by the number of numbers I looked at. And it's equidistributed or uniformly distributed if, as n gets very, very large, this approaches b minus a. So the probability I'm in the first half of the interval would just be 1/2. If I'm in the interval from 1/4 to 1/5, we can do fractions fast. 1/20th, exactly. Right. And so then the question is, of course, how do you prove something is equidistributed? That's hard. But the concept of equidistributed just means things fall uniformly. There's no tendency to cluster anywhere. Okay, so here's a theorem. Let me give you some number that's irrational. Then if I look at the multiples of beta, it's equidistributed modulo 1. So what does this mean? So I take some beta, I'll look at beta mod 1, 2 beta mod 1, 3 beta mod 1, and so on. So for each number I look at its fractional part, a number between 0 and 1, and I see how often that lies in the interval 0, 1/2. In the limit, that'll be 50% of the time. So whenever you see a theorem, you should always look at the conditions and ask, how important are they? So I'm assuming my number is irrational. What if I gave you a rational number like 1/5? Could a number like 1/5, could its multiples be equidistributed mod 1? Could they fall uniformly? No. I mean, I would have 1/5, 2/5, 3/5, 4/5, 5/5, which is 0, 6/5, well, mod 1, 6/5 is just 1/5. And I would just keep cycling through. So if I give you a rational number, you're only going to see finitely many values. So most of these intervals would actually be empty. And it's going to just come down to just what is the denominator. So it's absolutely essential that my number be irrational. So this is a fun problem to prove. Depending on whether or not you're a number theorist or an ergodic theorist, there's slightly different ways of interpreting what you're doing as to how you prove it. But it's a very nice result that any irrational number, its multiples are equidistributed modulo 1. So I'm going to need some numbers that are irrational. Anybody know any irrational numbers? E. Can you prove E is irrational?
Square root of 2.
Square root of 2. That's a much better one to prove. So the one I need is I need the log of 2 base 10 to be irrational, and I need the log base 10 of 1 plus root 5 over 2 to be irrational. So I won't prove this one. Anybody recognize this number? It's phi, the golden mean. So again, if you get bored during my talk, try to prove the log base 10 of 1 plus root 5 over 2 is irrational. I'll prove the log of 2 base 10 is irrational. If it's rational, well, that means this equals p over q, so 2 is then 10 to the p over q. Well, let's raise both sides to the qth power. So I get 2 to the q is 10 to the p, or 2 to the q minus p is 5 to the p. So I have some multiple of 2 is some multiple of 5. The only way that can work is if both sides are 1. So that means p has to be 0, and then q minus p has to be 0, so q has to be 0. So the only way I can get the log of 2 base 10 to be rational is if it equals 0 over 0. Okay. So the log of 2 base 10 is irrational. It's going to become very important later. So I was actually just talking with your professor before class about the advantages and disadvantages of methods to present. And one of the things that is a little bit unfortunate is when you prepare slides, you have to put in numbers already. So I can't ask you, give me your favorite irrational number. I chose one of my favorite irrational numbers, the square root of pi. It's a really nice irrational number. Okay? And so what I did is I looked at n times the square root of pi mod 1 for the first 10 values of n, and I saw how often did I get a number between 0 and 1/10, 1/10 and 2/10. Does the data look good? What do you really like about this data? Yes?
I mean, it's almost like...
Good, that was the word I wanted. Almost.
It's almost...
If everything was 1/10, you would think I'm rigging things. So I wanted something that wasn't quite perfect, so it looked a little bit more plausible. Alright, so checking the first 10 values is not really enough to see equidistribution be convincing. Let's go up to 100, 1,000, and then I do 10,000. If you have really good vision, you can see slight fluctuations in going up and down. But already at just 10,000 points, we're seeing very good equidistribution here. Okay, so here is the fundamental equivalence. This is how most people prove data sets of Benford. So I give you a data set xi. It's Benford base b, so if you want to think always Benford base 10. It's Benford if and only if the sequence of logarithms is equidistributed modulo 1. So what I'm really telling you is you have looked at data the wrong way all of your life. Whenever anybody gives you a number, the very first thing you should do is you should take its logarithm base 10 and then chop off the integer part. So when you get your exam scores back, I urge you to look at your exams in this manner. It'll then be interesting as to what a good score corresponds to. There'll be scattered distributions as to what that is. So why is this true? So here's a proof by picture. This image is extremely old. This is before I learned how to do subscripts and whatnot. This is embarrassing if anybody can figure out what program this was made with. So here's the interval from 0 to 1, and here's the log of 2 over log of 10. This is also known as the log of 2 base 10 by the change of base formula. Okay? Let's see what happens if I exponentiate. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the log of 2 base 10. What does that mean? I'm raising 10 to the number of powers of 10 I need to get 2. So if I raise 10 to the log of 2 base 10, I get 2. So every number from here to here, when I exponentiate, comes down to here. These are all the numbers whose first digit is 1. So the probability of first digit of 1 is equal to how often is your logarithm base 10 mod 1 in here. Well, let's assume now that your logarithm base 10 mod 1 and all that crap, let's assume that that falls evenly, that it's equidistributed, it falls uniformly in 0, 1. Well, then what's the percent of the time that I'm in here? The percent of the time I'm in here is the log of 2 base 10, the length of the interval. And so what we've just shown is that the amount of time I'm in that interval is the log base 10 of 2. And I can write that as log base 10 of 2 over 1. And if you think back to the original formula I gave you of the log base 10 of d plus 1 over d, this is where it's coming from. So at some point in high school, I think you were all given the log laws. Were you given any reason as to why you care about log laws? So when you see this, the log of 2 over 1, what should you be thinking of?
Log of 2 minus log of 1.
I'm sorry?
Log of 2 minus log of 1.
Good, log of 2 minus log of 1, the quotient rule. Let's say I want to have a first digit of d. Well, a first digit of d, it's the log base 10 of d plus 1 minus the log base 10 of d. Because these will be the numbers that exponentiate to a number whose first digit is between d and d plus 1. Oh, well now by log laws, that's the same as the log base 10 of d plus 1 over d. And that's really where the Benford probabilities are coming from. It's coming from a subtraction. That's where the quotient is coming into play. So you can go back and forth in terms of these equivalencies, but this is essentially the best way we have of proving Benford behavior. That if my sequence is Benford, then the logarithms base 10 modulo 1 are equidistributed, or conversely, if these are equidistributed, my original sequence is Benford. So now we can prove 2 to the n is Benford base 10. Why? Well, if my original sequence is just 2 to the n, then I look at its logarithm. So xn is 2 to the n. So yn is the log base 10 of xn. That's n log base 10 of 2. And from our earlier result, this is an irrational number, and we know that the multiples of an irrational number are equidistributed. So we now know that 2 to the n is Benford. Okay? Here's another example. The Fibonacci numbers are Benford base 10. So I'm going to assume everyone has seen the Fibonacci numbers. If not, just nod your head. Okay, so they're given by the relationship an plus 1 is an plus an minus 1. I'll actually be talking more about the Fibonacci numbers at 4 today. So my favorite way of proving what the nth Fibonacci number is the method of divine inspiration. It's a wonderful method to solve math problems. You write down the correct answer, and then you show that's the correct answer. It's unfortunately a very fickle method at times, especially as you continue in your career. But if you then go to earlier classes, it's much easier to use. So let's just guess that the nth Fibonacci number is r to the n. And this is where the Boston accent may make things a little hard, but r to the n plus 1 is r to the n plus r to the n minus 1, or canceling you get r squared is r plus 1. Well, if you solve that, you get two roots. R is 1 plus or minus root 5 over 2. And then what you notice is that this is a linear relation. If r to the n is a solution, I could multiply it by 5 and it will still be a solution. Because I can just cancel the 5s on both sides. And if I take two solutions and I add them, I get a solution. So any solution to this can be written in the form some constant first root to the nth plus some other constant second root to the nth. And you just have to figure out what are the choices of these constants. Well, if I know the first few values of the Fibonacci numbers, I can use that by linear algebra to figure out what those numbers are. And we get Benet's formula. And to me, this is always a miraculous formula. What can you tell me about the nth Fibonacci number? What kind of number is it?
It's an integer.
It's an integer. I've got square roots of 5, I've got divisions by 2, and yet it's always going to be an integer. What's nice is this number is greater than 1 in absolute value, this number is less than 1 in absolute value. If n is very large, this number is essentially 0. So the nth Fibonacci number is essentially whatever number is closest, whatever integer is closest to this. And it's going to be extremely close. Okay, well, how do I prove things at Benford? All I have to do now is just take this number and look at its log. And so this is where you have to roll up your sleeves and do a little bit of technical details. Will you all agree that I can just drop this because this number is going to be so small? This is where basically number theory is a lot like accounting. You just have to carefully work with the books and show that this really won't change many of the digits. Now if I take logarithms, what do I get? Well, I get the log of a product is the sum of the logs. So I'll get n log 1 plus root 5 over 2 plus the log of 1 over root 5. If this is uniformly distributed, if this is equidistributed, then if I just shift everything by the same amount, it's still going to be equidistributed. So all I need to do is show that this is equidistributed. All I need now is that this is an irrational number, the log of 1 plus root 5 over 2. Well, this is one of the things I told you, to be playing with if you get bored. And so it's a nice exercise. Prove that the log of the golden mean base 10 is irrational, and now you essentially have the Fibonacci numbers. So this argument works not just for the Fibonacci numbers, but for almost all recurrence relations. You've got to be a little bit careful. There's a couple of counterexamples. One example that works is something we've already done. an plus 1 is 2an. That's going to give us the powers of 2. If I look at this relation, though, it's not going to be Benford. And so it's something to think about. Why is this not Benford? And I'll give you, I'll make these slides available, some interesting starting points which will lead to non-Benford behavior. Alright, so now we're going to pretend to be representatives of the IRS. You're given the following data set, powers of 2 to the n. You're told that this is supposed to be Benford. And here's the observed probabilities, here's the Benford probabilities. Do things look good? Do things look Benford? If not, what looks bad? What looks suspicious?
The last 3 digits.
The last 3 digits. Anyone in particular bother you?
8.
8. Anything else?
9.
9. I think 9 is, to me, 9 bothered me the most. But I can see 8 being bad. I think just percentage-wise, this was the worst error for me. But here's the thing, I've given you a theorem, so either A, I've made a mistake, and that could be another reason why I'm no longer brown. Or what else? What could be going on? You need more data. So I've calculated the first 60 values, I'm only displaying 30. Anybody notice an interesting pattern on the left? Look at the numbers on the left. It's not a coincidence how they're grouped. So I'm going every 10. 8, 8192, 8388, 608. Any computer scientists here? No, I thought I had even more. I had more earlier. Okay. How many megabytes are there in a gigabyte? 1024, right? If the computer scientists really understood the Greek and Latin, mega to giga should be a factor of 1,000, right? But they have 1,024. So it's not that the computer scientists don't understand Greek and Latin. That's a different issue. They understand something more important, that computers work base 2. And so looking at things base 2, 2 to the 10 is 1024, is approximately 10 cubed. And so every time you go 10 steps, 10 iterations, you almost return to where you start. You're off by about 2.4%. Eventually, Benford will kick in, but the rate of convergence is going to be slow because of this. And that's one of the things the IRS really cares about. How many data points do they need before they can be reasonably sure that something is going on? And so the rate of convergence is, for those who care about number theory, is actually related to algebraic properties of how irrational the logarithms are. And so this is a fun area of research. And so, how many of you have seen chi-square tests? Okay, so basically a chi-square test measures how good of a fit something is. The larger the chi-squared value, the worse the fit. And so I chose 3 numbers: the Euler-Mascheroni constant gamma, e, and pi. And I looked at the first n values of basically gamma to the n. And now if you notice, one of the numbers is looking like it's having a hard time fitting Benford. Which one? Pi. So as you all know, pi to the 175 is approximately 1.0028 times 10 to the 87. Because I know you've all calculated not just digits of pi, but powers of pi. So what this means is every time you go through 175 iterations, you've almost padded yourself by 87 zeros. And so if you look at the goodness of fit, notice that the length of these things is approximately 175. It's detecting that there's an integer power of pi that's very close to a power of 10. Alright, so in the last 5 minutes, I want to talk a little bit about some of the applications of Benford's law. So one of my colleagues is an accountant, and he likes to say it's fascinating what the Freedom of Information Act and a couple $100 will buy you. So this is the 1989 individual tax return of somebody named William J., who's married to somebody named Hillary. They're from a place called Little Rock, Arkansas. And so you're absolutely amazing what the Freedom of Information will get you. I don't know if that will still be true in a few years, but there's some comments over here that if you want to view, you might enjoy. I will again make these slides available. Here's the 1992 version. The address has changed. Alright. So here's a fun example. A bank has been audited, and a huge spike has been found. So this is a credit card company. So they looked to see how many times they have a first digit of 1, of 2, of 3, etc. And they found one number occurring statistically more often than Benford predicted. Anybody know what number that is?
What data is it?
I'm not telling you. You've got a 1 in 9 chance.
9.
9.
No.
1.
No, higher.
10. 5. 7.
Lower than 5.
3.
3.
A little higher.
4.
4, yes, very good. Starting with 4. This then credit card company, they investigated further. Once they had the spike of 4, they looked at the second digit. And most of the 4s, their second digit was one of 2 numbers. Any thoughts for those numbers?
9.
Good. See, that was much faster. 48 and 49. And they traced most of the spike to one person who was working for the company. Any thoughts what I'm talking about?
Like the lunch thing.
It's similar to the lunch thing. What happens if you lose a credit card? Well, if your credit card is stolen. What do you do if your credit card is stolen?
You cancel it.
You cancel it. And are you liable for the purchases? No. So imagine you are a huge multinational bank, and someone calls up, their credit card's been stolen, there's $120 in charges that they claim are not theirs. How much money are you willing to spend to track down $120 in charges? How much? It's going to cost you a couple $100 just to open up a case on this. Are you going to spend your time as a multinational bank investigating $120?
No.
No. What if it's $20,000? Oh, now we're talking some more. Okay, so you need a cutoff value. Anything below this cutoff value, you're not going to bother investigating. Anything above, you will investigate. Anybody want to guess what that cutoff value is?
500?
Not 500.
5,000?
5,000. So anything, there's a write-off limit of $5,000. What the officer did is he had his friends applying for credit cards. He would have his friends run up balances and then call and claim that their credit card had been stolen. He would answer the phone, oh, your card has been stolen. Oh, I'm so sorry to hear that. Oh no, don't worry, you're not liable for any of the charges. And he kept it below the critical threshold that would generate an internal audit by the bank. And so he'd been doing this for quite a while. And the way he was caught is, he got greedy, he did it so many times, there was a noticeable spike at the 4s and the 4.8s, 4.9s. And then once you know where to investigate, then you start uncovering the things. And so this allowed the auditors to zero in exactly where they should. Here's another fun example. My colleague is a professor of accounting, I'm a professor of mathematics, so clearly we should write a paper in geology. So why do we look at geology? Well, streamflow data really hasn't changed that much in 130 years in terms of measuring how much water there is. And so we have a data set that goes across many, many years, has almost 500,000 records. And so streamflow data is a beautiful fit with Benford's law. I think there's one last one, election fraud in Iran in 2009. And so I don't know if you remember the Iranian elections, but the evidence is a little bit mixed as to whether or not there was fraud there. One of the questions is, what kind of test can you do? You can look at first and second digits. Good test to use here is actually to look at the last digits. Is, how often are the last two digits, 5, 5, 6, 6, 7, 7. There should be a repeat roughly 1/10 of the time. And so if people are just making up numbers, people often make up numbers incorrectly. And so there's evidence indicating the Iranian elections are suspicious, but not enough. We just had presidential elections here. Were the presidential elections here fraud or no fraud? There are some places where there were more votes than registered voters. So clearly there has been some fraud recently. The question is, I always feel, not that I love being fair to Iran, but if I'm going to point out what's going on in Iran, I should point out what's going on close to home as well. Sometimes you really do not need powerful tests to detect fraud. If you have more votes than voters, it's clear something has happened. And so, right now there are places in Florida with 140% above the number of registered voters. Colorado has a bunch of places at 109% plus. It's quite clear something has gone on in those places. It's a very interesting application of Benford's law to detect fraud like this. So one of the things I love about Beam is the ability to just quickly jump to the end. So just quickly end. There's a search for more sophisticated tests for fraud. And so I'm working with the IRS to develop some of these. This will be projects for future. There's other kinds of systems you can study. One of the things I'm interested in, which has applications to statistical mechanics and physics, is what happens if you break an object and you keep breaking it. What happens to the distribution of fragments? And so it turns out that in certain situations we can prove that this is Benford. We think this will hold in greater generality. So thank you for your attention. If anybody has any questions, please feel free to shoot me an email. And it was great to be back.